If you feed the word silent into a state-of-the-art artificial intelligence, and then scramble those exact same letters to spell listen, the underlying engine sees no difference. To the raw mathematical core of models like GPT-4 or Claude, those two words are identical. They contain the exact same elements, so they are processed as the exact same thing. Without a specific mathematical hack, the most powerful artificial intelligence systems on Earth are completely blind to sequence, order, and time. This is the starting point of the transformer architecture. We assume these models read like humans, scanning left to right, building context as they go. But they do not. Left to its own devices, a transformer treats a Shakespearean sonnet and a randomized word soup of that same sonnet as the exact same document. This is the phenomenon of permutation invariance, and it is the single greatest design flaw, and paradoxically, the greatest strength of modern AI. To understand how we got here, we have to look at how older AI architectures processed information. In machine learning, we talk about inductive bias. This is simply the set of assumptions we build into an algorithm to help it learn. Older vision models used convolutional neural networks, which have a built-in bias for locality. They assume that pixels close to each other are related. Language models used recurrent neural networks, which have a built-in bias for chronology. They process words one by one, step by step, much like a tape recorder. This made them great at understanding order, but terrible at scaling. They could not look ahead, and they could not parallelize their workload. When researchers introduced the transformer in 2017, they threw all of these assumptions away. They built a system with zero sequence-based inductive bias. A transformer processes every single token in a document simultaneously. It has no concept of before, no concept of after, and no concept of distance. It is a completely blank slate. Because a raw transformer has no innate sense of order, researchers had to find a way to manually inject it. This is where positional encoding comes in. In the original 2017 paper, Attention is All You Need, the authors introduced a remarkably elegant solution. They used trigonometry. Before feeding a sequence of words into the attention engine, they calculated a unique mathematical coordinate for each position in the sentence using sine and cosine waves of varying frequencies. Think of it like stamping a physical envelope. Instead of just writing the message, you stamp a set of latitude and longitude coordinates onto the paper itself. These trigonometric waves operate at different wavelengths, allowing the model to distinguish between the first word in a document and the 10,000th word. The model does not read the words in order, but it can look at the coordinate stamps to reconstruct where each word belongs. This is absolute positional encoding. For a few years, absolute positional encoding worked perfectly. But as AI models grew and users started feeding them entire books instead of short paragraphs, this approach hit a wall. The problem is extrapolation. If you train a model on documents that are 4,000 tokens long, it learns to recognize coordinates from 1 to 4,000. But what happens when you feed it a document that is 10,000 tokens long? The model encounters coordinates it has never seen before. It has no idea what to do with a wave value at position 8,000. The coordinate system simply breaks, and the model output devolves into gibberish. This is the extrapolative wall. Absolute coordinates fail because they are tied to a fixed grid. If you change the size of the room, the coordinates lose their meaning. To break through this wall, researchers had a massive realization. When humans read, we do not care if a word is exactly at position 47,000 in a book. We care about how far that word is from the words around it. We care about relative distance. This sparked the relative positional encoding revolution. Instead of stamping every word with an absolute coordinate before it enters the model, relative encoding schemes inject distance information directly into the attention mechanism itself. As the model calculates how much attention one word should pay to another, it adds a penalty or a bonus based on how far apart they are. If two words are side by side, they get a strong connection. If they are paragraphs apart, the connection is mathematically dampened. This allowed models to generalize to much longer sequences than they were trained on, but it came with a massive computational cost. Measuring the distance between every single pair of words is incredibly expensive. The breakthrough that solved this trade-off is the standard for modern AI models today, from Meta's Llama to Mistral. It is called rotary position embedding, or rope. To understand rope, imagine a clock face with two hands. Instead of trying to measure the distance between the hands with a ruler, we look at the angle between them. In the mathematical space of the model, every word is represented as a vector. Rope works by taking these vectors and rotating them in a multidimensional space. The amount of rotation corresponds directly to the word's position in the sequence. If two words are close together, their vectors are rotated by similar amounts, meaning the angle between them is small. If they are far apart, the angle is large. Because dot products between vectors are naturally sensitive to angles, the attention mechanism can instantly read the relative distance between words just by looking at how they are rotated. It is an incredibly elegant fusion of absolute position and relative distance, all achieved through simple geometric rotation. But just as we solved this for text, the frontier of AI shifted to video. Models like Sora and other physical world simulators have exposed a massive scaling bottleneck. Text is one-dimensional. It is a single line of words. Video is three-dimensional. It has height, width, and time. When you break a video down into small visual patches to feed into a transformer, you are no longer dealing with a simple sequence of words. You are dealing with pixels that have spatial relationships to the left, right, up, and down, alongside temporal relationships to what happened frames before and what happens frames after. Because transformers have no built-in inductive bias, they do not inherently know that a patch of a car wheel in frame 1 is connected to the same wheel in frame 2. Trying to represent these complex, multidimensional geometric relationships without melting the hardware has become the primary battleground of modern AI engineering. Our current mathematical hacks are being pushed to their absolute limits. This reveals the ultimate trade-off of modern artificial intelligence. By stripping the transformer of all built-in assumptions about time, space, and order, we created a model of unparalleled flexibility. A transformer can process text, images, video, genomic sequences, or audio, because to the model, everything is just an abstract set of relationships. It is a universal computer. But the price of this absolute freedom is that we must constantly pay for it in compute. We must build increasingly complex mathematical scaffolding just to teach the machine what we learn as children, that sequence matters, that time moves forward, and that order defines meaning. The intelligence of these models does not just come from their scale. It comes from the invisible, clever geometry we use to anchor them to our reality.